Welcome to the Deep Dive. We take fascinating research, break it down, and give you what you need to really get it fast.
Yep, get you up to speed.
So today, we're digging into a paper. It's from, 2017, but still super relevant. Variational Lossy Autoencoder.
That's the one. And our mission today, yours and ours, is to understand this method they came up with for learning data representations. We're talking mainly images here.
Right.
But the key thing is it lets you control what information gets captured. Like imagine wanting the overall shape of something, but maybe actively throwing away the texture details.
Okay, yeah, that's interesting. So it's all about representation learning, getting the data into a form machines can actually use better, maybe for classification or something.
Exactly. And ideally, you want to tease apart the underlying causes. What's the main thing in the image versus its particular style? Things like that. You're often less interested in like every single pixel.
So a common way to do this, the paper mentions, is using these probabilistic latent variable models, kind of learning by trying to generate the data.
Yeah, analysis by synthesis, that's the idea. You build a generator, and the hidden or latent variables it uses become your representation. But, and this is a big but, just being able to generate the data isn't enough. Turns out lots of models can create images that look okay, but they haven't actually learned a useful representation of the structure underneath.
And that's different from those really powerful AI image generators we see everywhere now, the autoregressive ones.
Right. Those are amazing at generation because they build the image piece by piece, like predicting the next pixel based on the previous ones.
Yeah,
Super powerful.
but not traditionally used for this kind of representation learning.
Not so much. Their structure, how they learn, it doesn't naturally give you that clean separation of factors, that sort of latent hierarchy you often want for representation tasks.
Okay, so here's the puzzle the paper tackles. Can we get the best of both worlds? A model that's really good at density estimation, understanding the data's probabilities, and has the right internal setup for learning good representations.
Precisely. And their answer, the spoiler, is a kind of hybrid model. They combine the latent variables from a VAE, that's a variational autoencoder, with the sheer power of those autoregressive models.
Okay, let's unpack that, starting with the standard VAE. Why isn't it always the complete answer? People often describe them as just autoencoders, right? Trying to copy the input, but with some extra rules.
That's a common starting point, yeah. But it's crucial to get that VAEs aren't really trying to make perfect copies. That's not the main goal.
Ah, okay. So what is the goal? It's tied to that math thing, the variational lower bound, right?
Exactly. That lower bound, or ELBO, is basically a stand-in and approximation for how likely the data is under our model. The paper gives the equation, Lx equals the expected log probability of x given z minus the KL divergence between QCX and PC.
Whoa, okay. Let's break that down. The first part, expected log PAEA. That's like the reconstruction quality.
Sort of, yeah. Given the compressed code Zias that our encoder QZX produced from the input X, how well can our decoder PSC generate something that looks like X? So, yeah, related to reconstruction.
And the second part, the DKL thing.
The KL divergence. DKL QZX PZ. Think of it as a penalty or a regularizer. It measures how much our learned encoding distribution, QZX, deviates from some simple prior belief we have about what the code should look like, PZ, usually just a simple Gaussian. It keeps the codes from getting too wild.
Got it. And the paper said for images, if you use a simple decoder, like assuming pixels are independent.
A factorized decoder, yeah. PXZ is just the product of PVC for all pixels I.
Right. If you do that, you often get sharp-looking reconstructions.
Often, yes. Because the model can focus on predicting each pixel pretty well, just based on the code Z. It doesn't need complex dependencies between pixels in the decoder itself.
Okay, so VAEs aren't just about copying. Now this information preference idea, what's that about? Sounds key.
It really is. This is where it gets subtle. What happens if you make the decoder PXC really powerful, like say using an RNN or something similar, with autoregressive connections?
Meaning each pixel prediction depends on the code Z and the pixels generated before it.
Exactly, like painting step by step, looking at what you've already painted. These models are super flexible. They can, in theory, model almost any data distribution.
Okay, what's the catch?
The catch, and this is the core observation, is that when you pair a standard VAE setup with one of these super powerful autoregressive decoders, the model often just learns to ignore the latent code Z.
Wait, ignore it. Why would it do that? Isn't Z supposed to be the important representation?
You'd think so, But the autoregressive decoder becomes so good at predicting the next pixel just based on the previous pixel that it doesn't need the global information summarized in Z. It takes the easy path, essentially becoming just an unconditional autoregressive model.
Huh. So the representation learning part kind of fails.
It can, yeah. The paper uses this information theory view, bits-back coding, to explain it. Think of encoding X in two stages. First, encode X into Z using our encoder QX. Second, encode the difference, the error, between X and what PXC can reconstruct.
Trying to be efficient, right? Minimize the total code length.
Exactly. Bits-back coding is a slightly more clever version where the encoder QZX itself helps transmit some information, effectively shortening the total code length needed.
And shorter code length is better.
Better model, yeah. It turns out the expected code length in the scheme is exactly the negative of the VAE lower bound, dash LX. So minimizing code length is maximizing the lower bound. Same goal.
Okay, so the formula they give, C bits back X, expected value of log QZX, log PXZ, that equals SXX.
Right, and the crucial insight is that the latent code Z only gets used if doing this whole two-part coding, encoding Z then encoding the rest using PX plus the bits back saving, is more efficient than just modeling X directly.
More efficient than what the decoder PAV could do on its own.
Precisely. There's a theoretical minimum code length, the data's entropy. VAEs have an inherent inefficiency related to the gap between the approximate encoder, QZX, and the true, but usually intractable, posterior, PZX. That gap is a KL divergence, DKL, QZX.
So the information preference, if the powerful autoregressive decoder, PAC, can model the data really well without needing Z, it will basically sideline Z to minimize its part of the coding cost.
That's the essence of it. The decoder preferentially models whatever information it can handle easily with its structure, typically local dependencies if it's autoregressive, and only forces information into Z if it absolutely has to.
Which is why Z gets ignored when the decoder is too powerful.
Exactly. The information prefers to be captured by the powerful autoregressive likelihood term PAC, rather than going through the Z bottleneck represented by the KL term.
The paper mentions people tried things to force the VAE to use Z, right? Like simple decoders or KL annealing. Free bits.
Yeah, those are techniques. Using a simple factorized decoder forces ZIN to carry more weight. KL annealing slowly ramps up the importance of that KL penalty during training, encouraging ZIN to become more structured. Free bits gives some dimensions of ZIN a grace period, letting them pass information without penalty initially to prevent the KL term from just crushing ZIN to zero right away.
Okay, so that sets the stage. Standard VAEs plus powerful decoders ignored ZIN. Now enter the variational Lossy autoencoder, VLAE. How does it fix this?
It's clever. It uses autoregressive models in two key ways. One is to control the representation, make it lossy in a specific way. The other is to actually improve the density estimation.
Let's take the first one, the lossy code via explicit information placement. How does that work?
It flips the information preference problem on its head. If the decoder preferentially models certain kinds of information, let's design the decoder so it's good at modeling the stuff we don't want in our main representation ZIN, but bad at modeling the stuff we do want.
Whoa, okay, so you cripple the decoder strategically?
Kind of. For instance, say you want global shapes in Z, but want to ignore local texture. You design an autoregressive decoder, PTEX-C, that has a very small receptive field.
Meaning when it predicts a pixel, it only looks at a tiny patch of neighbors, not the whole image generated so far.
Exactly. Like Plokadex-C, product over I of PTEX-C X window around, because it only sees a small local window.
You can probably model texture pretty well just based on those neighbors, right?
Yeah.
Texture is often local patterns.
Precisely. It can capture those local statistics easily. But modeling the overall shape of an object requires seeing long-range dependencies across the image. This locally blind decoder can't do that well on its own.
So if the decoder can't model the global shape, that information has to be pushed into the latent code Z.
That's the trick. By limiting the decoder, you force the information it can't handle into the representation Z you care about. It's lossy because the decoder is handling and potentially discarding details about the local stuff.
And you could change the receptive field size or structure to capture different things, like maybe downsample the window to focus Z on finer details.
Absolutely. The constraint you place on the decoder determines what kind of information Z is forced to represent. It's controllable lossy compression.
Very cool. Okay, that's the lossy part. What's the second autoregressive trick? The learned prior with autoregressive flow. AF.
So this tackles the other issue, the inefficiency in the VAE, that gap between the approximate encoder QZX and the true posterior PZX, which hurts the overall model quality, the density estimation.
Right, minimizing that KL divergence, DKL, QZX, PZX.
Well, minimizing it directly is hard. Instead, they focus on the other KL term in the lower bound, DKL-QZX.
Okay.
They make the prior, PZ, much more flexible and expressive using an autoregressive flow.
An autoregressive flow. That's like those normalizing flows, building complex distributions from simple ones using invertible math.
Exactly. They use invertible autoregressive transformations. Think inverse autoregressive flow, IAF, which is a known, powerful type of normalizing flow.
So how does using an autoregressive flow for the prior PZ help?
The neat mathematical insight is that using an autoregressive flow for the prior PZ is equivalent to using an inverse autoregressive flow for the approximate posterior QZ.
Equivalent, how?
It's in how the terms rearrange in the lower bound calculation. The upshot is, by making the prior more complex with an AF, you effectively get the power of a very complex encoder, like an IAF encoder, which helps close that inefficiency gap and improves the overall model likelihood. Kind of for free, computationally speaking, compared to explicitly using a complex IAF encoder.
So a flexible AF prior leads to a better generative model of Z, which indirectly makes the whole VAE better at modeling the original data X.
That's the idea. Better prior, better ELBO, better density estimation.
Okay, so VLAE, controlled lossy code via limited decoder, plus better density estimation via flexible AF prior. Makes sense. How did it actually perform in the experiments? They use image data sets, right? MNIST, CFAR?
MNIST, Omniglot, Caltech Silhouettes, CFAR10, and they used Pixel CNN, which naturally has that local receptive field as their conditional decoder PXE.
So first, the lossy compression. Did it work? Did ZAZ capture less information?
It did. On MNIST, the VLE needed significantly fewer nats, a measure related to bits in its latent code, compared to a standard VAE, about 13.3 nats versus maybe 37 bits for a comparison VAE, so definitely lossier.
And the pictures, did they look like they kept the shape but lost the texture?
Yeah, the visualizations were pretty clear. Original MNIST digits versus the VLE reconstructions, the overall digit shape was there, but the exact pixel patterns, the sort of handwriting texture was different, smoothed out or changed. It captured the what, but not the exact how.
But you mentioned Omniglot was trickier.
Right. Omniglot has characters where fine details matter for meaning. The VLAE sometimes lost semantic information there, showing that what gets kept depends heavily on the decoder design and the data itself. It's not magic. It depends on whether the decoder can effectively separate the information you want from the information you don't.
Makes sense. Okay, what about the other goal density estimation? Did the AF prior help?
Yes. Comparing a VAE with the AF prior versus one with an equivalent IAF posterior showed the AF prior version performed better, supporting their theory, and the full VLAE model, with both the Pixel CNN decoder and the AF prior, set a new state-of-the-art score on MNIST density estimation at the time.
Wow. Was it just good on MNIST?
Nope. Impressively, they used the same VLAE model setup, and it performed really well across several datasets, dynamically binarized MNIST, Caltech Silhouettes, beating previous results significantly, and tied the best on Omniglot. That's quite robust.
And compared to just training the Pixel CNN decoder directly?
The VLAE approach generally did better, suggesting the latent variable framework was adding value beyond just the powerful decoder.
What about the harder datasets, CYFAR10, natural images?
Still strong results. VLAE was state-of-the-art among similar variational models and held its own against other types of likelihood models. They used more advanced backbones, like ResNet inside the VAE, and developed a combined KL annealing free bits training strategy for stability.
And did they show the lossy compression working on CIFAR10 too, with different receptive fields?
They did. They showed reconstructions using Pixel CNN decoders with different window sizes, like 4x2, 5x3, 7x4. As the window got bigger,
the decoder could capture more structure locally.
Exactly. So less detailed shape information ended up being stored in the latent code Z. It visually demonstrated that trade-off. Give the decoder more power locally, and Z becomes less informative about those local structures.
That really drives the point home in that grayscale experiment.
Oh yeah, that was neat. They made the Pixel CNN decoder only look at grayscale neighbors, so it couldn't possibly model the color information itself.
Forcing the color into Z.
Right. And the reconstructions kept the structure and the color because the color info was now encoded in Z. It showed you could explicitly choose what information gets sidelined by the decoder and thus preserved in the latent code.
Very clever. Did they mention related work? Was this idea completely out of the blue?
Not entirely. They situated it within other research combining VAEs and autoregressive models, especially for things like text, and work on autoregressive latent variables and lossy coding. They also acknowledged simultaneous work like pixel VAE, which had some overlapping ideas.
Okay, so wrapping up the paper's contributions, VLAE gives you. What are the big wins?
Two main things. First, controllable representation learning. By designing the decoder's limitations, like receptive field, you can influence what information gets captured in the latent code Z's, enabling targeted lossy compression. Second, improved density estimation, largely thanks to using that flexible autoregressive flow prior for PS.
Any downsides?
The main one is generation speed. Because the decoder is autoregressive, generating new samples involves predicting pixels one by one, which is slower than decoders that generate everything at once.
And future directions.
They suggested extending it to sequential data like audio or video and designing task-specific lossy representations, maybe for semi-supervised learning where you only have labels for some data.
Okay, so let's boil this down for everyone listening. The big takeaway from this variational lossy autoencoder paper is this really smart way to blend VAEs and autoregressive models. They use that weird information preference where a strong decoder might ignore the main code to their advantage by deliberately limiting what the decoder can see or do.
Usually by restricting its receptive field.
Right. You force the information you actually care about, like the big picture structure, into that compressed latent code ZIA. Meanwhile, the decoder handles and maybe discards the less important stuff like fine texture.
It gives you a knob to turn, basically, a principled way to control the trade-off between compression and retaining specific kinds of information.
So you get a more focused, potentially more useful representation.
Exactly. Instead of just hoping the standard VAE finds something useful, you guide it.
Okay, so here's the final thought to leave you with. This idea of deliberately shaping what information gets encoded and what gets filtered. How could that apply elsewhere? We talked images, but what about audio?
Yeah. Maybe focusing on, say, speaker identity while ignoring the specific words, or vice versa.
Or analyzing complex scientific data, focusing on anomalies while filtering out baseline noise. Even understanding text, maybe pulling out the main sentiment while ignoring specific phrasing.
It really opens up possibilities. Where could this kind of intelligent lossy compression, this information filtering, be most valuable for understanding complex data for you? Something to chew on.
Definitely something to think about. Thanks for joining us on this deep dive into the variational lossy autoencoder.
Thanks for listening.
Until next time, keep digging deeper.